Hello everyone, welcome to this video. In this video we're going to be looking at a comparison between hand calculations using Castigliano's theorem and an analysis in S-FRAME, where we're going to be looking at a truss structure, in this case here a simple 3-element truss structure that is 5 meters high, 3 meters wide, and we're specifically going to be looking at finding the vertical displacement at point C. And with our hand calculations, we can use the Castigliano theorem, which is applicable for linear analysis to determine the displacement or the slope at a point. And if you're not familiar with this theorem, it's basically used if a displacement at a point, or of a point, is to be determined. It can be found to be equal to the first partial derivative of the strain energy of the structure with respect to a force that's acting at that point in the direction of the displacement. So for our problem statement here, you can see we've already mentioned the dimensions 5 meters high, 3 meters wide. These are all assumed to be truss elements, meaning that they only have axial stiffness. The cross-sectional area of our sections is 200 square millimeters, and we know our material properties as well, 200 GPa for steel. We have a lateral load of 1 kilonewton. We have a simply supported span for the base of our truss, and we're going to be looking at finding the vertical displacement at point C here. Now, in order to follow through with the Castigliano's theorem, we need to apply that force that's acting at the point in which we want to determine the displacement. So that force is going to be equal to P, we're just giving it the value P for now, at point C. And again, we're looking at the vertical displacement, so we want that to be going in the vertical direction. And with this force P and the existing 1 kilonewton load that we have, we can determine the reactions. So naturally, the lateral reaction is 1 kilonewton, that's just resisting this 1 kilonewton force at the top at point C. And for our vertical reactions, we have the value of P factoring in, as well as the reactions from this 1 kilonewton load eccentric to each one of these points. Now we want to determine the internal forces at our truss supports using the method of joints, and we can determine the forces in each one of the elements. So we can break this down into joints at joint A and joint B, knowing the slope of the trusses that we have and the reaction loads that we have on our model. And we're able to define the internal forces. So in the axial load in A to B is equal to 0.15 B plus 0.499. That's in tension. The other two are found to be in compression, as you can see, with the basically mirrored values of one another, with the exception being that this is a plus 1.74, this is a negative 1.74 on A to C. So if we put this into a tabular format here, we can look at the different n values, the axial loads in our trusses, and the partial derivatives as well. Now, if we set n equal to, if we look at n when we set P equal to 0, because P isn't actually a real force in our structure, we're going to set that equal to 0. We'll find that n equals 0.499 for A to B, 1.74 for A to C, and B to C is negative 1.74. So these negative signs are important, and we've actually retained those in this n cell here. The length we just found through basic trigonometry. We could found it through just measuring it as well. It varies between 5.83 meters and 3 meters. And you can see here, once we plug it into this equation, we find the sum to be equal to 0.224 kilonewton meters. And this is helpful because we want to plug this into Castigliano's theorem, where we actually know pretty much everything in this already is just found in this summation here. We're just going to divide by our section property, our area of our cross section, and our Young's modulus. And we can find here, with all the information that we have, that the displacement at point C in the vertical direction should equal to 0.0056 millimeters. So we're going to go into S-FRAME, rebuild this model from scratch in S-FRAME, and solve it and determine how close we're getting to our expected values. So I'm in a 2D model in S-FRAME right now, and the first thing I want to do is just draw out my joints. And I think the easiest way to do this, since I only have 3 joints, is just to use the joint tool and type in the coordinates. So I'm going to have a coordinate, or a joint, coordinate x equals 0 and y equals 0. So I'll just click OK, because that's already filled out in my coordinate fields here. we can see I have a joint 1 right there. The next joint is going to be joint on the right hand side, which is going to be 3 meters in the x-axis away from the first joint, so I'll click OK. And then the third joint is above the other two, in between in the x-axis, so x equals 0 or 1.5 and y equals 5 meters. Now I'm going to use the member definition tool to connect these, and I'm just going to specify that this is a member type truss, not a beam. The difference between the two is that a truss member can only support axial loads. It has axial stiffness only, whereas a beam can support moments. It has bending stiffness, shear stiffness, and axial stiffness. So obviously we can apply releases, but that's the default conditions. So with this set here, I'm just going to left click and sketch out my truss diagram here. And now we've got what I like to refer to as the skeleton of our model. We still need to apply some additional properties. I'll first look at our material properties. And you can see here that by default, material 1 is assigned to all members, which is handy in this case. It's a steel material, but I want to right click and look at the material properties a little bit closer just to make sure it's using the ideal Young's modulus. So I'll click on steel US and Canada, and here we can see that it is using the Young's modulus that I wanted, the 200 GPa. Under the section property, I don't have any section properties in my model yet, so I'm going to define those now. I'm just going to define one. And you can see here, we can just give it a section name. I'm going to call this truss. And I'm going to fill out just some arbitrary values for moments of inertia and shear area. It doesn't really, it's not important what we enter here because we're using truss elements, so those aren't really going to factor in anyways. They don't have any bending or shear stiffness. But the gross area is important. I'm going to say that it's 200 square millimeters. And I'm just going to click add to add this to my model. And you can see section 1 is added to all the members by default. Now we need to consider our supports. So I'll just left click on the support tool. And actually maybe I'll right click just to get the diagrams that we might be used to seeing. I may recall that I have a simply supported truss. So on the bottom left here, I'm going to have a pin, which I'm going to set as this condition here. I'll left click on that and click OK, and you can see here when I set that pin condition, it's toggled on the TX and TY, which is translation X and Y restraints, and it's leaving RZ unrestrained. And I just need to left click and drag around the joints I wish to apply that support condition to. And you can see here that's representing the pin condition. And we can do the same thing. I can right click again and I can look for the roller that I want, which is this one here. I'll click OK, and you can see I could have also just left clicked and toggled off this TX restraint, but now I have TY restrained here, and I'm just going to left click and drag, and you can see this joint is now constrained so that it won't be able to move up and down, but it will be able to move side to side and obviously rotate because I don't have TX or RZ restraint. So with that done, let me save the model. I'll go File, Save As. And I'm just going to save this with a descriptive name. And once I've saved that model, I can go to the loads window and I can create a load case, which I'm going to call lateral. I don't need to worry about applying that P load. Obviously, that isn't a numerical value that I can apply anyways, but that load was just part of the process that's described in the Castigliano's theorem. However, for S-FRAME, I can actually just simply apply that lateral load directly and observe the displacements directly through a finite element analysis. So here I'm going to click on the joint load tool. I specify which direction I want my joint load to be in. I'm going to say in the X force direction. And I specify the magnitude, which in this case here is 1 kilonewton. And I can just left click and apply it to the top joint in my model. And I'm now ready to go ahead and run my analysis. So click the Analyze button. If you haven't seen that one, it looks like 2 footsteps. You can also access the same thing from the Run menu and click on Analysis. And here I have the option to select what type of analysis I'd like to run and whether I'd like to solve for load cases, combinations, or both. I just have a single load case in this model, so as long as I select that I either want to solve for my load cases or both, that will be fine. And I'm going to run a linear static analysis like I mentioned earlier. So I'll click OK. When I run this analysis, you can see here that we are getting a clean solution. We're not getting any diagnostic messages. However, if we did, we could always look those up or contact S-FRAME support if you need additional assistance with that. But here I can see the analysis is solved. I'm in the graphical results window rather. And the first thing I want to look at is the deflections. So the deflections, I can see how this is deflecting. It shouldn't come as a surprise that it's deflecting to the right. That's the direction that the load is pushing it in. I can see the dx displacement value at the joint locations by just left clicking on this toggle here. And I can see dx is going about 0.81 millimeters to the right. And I can also look at dy. But I might want to see a little bit more detailed view if I go to the right, click on this joint, and I go to properties. Here I can actually see in more detail that I'm getting 0.0056 millimeters. The reason for the discrepancy, what we see here, is just a personal setting that I had made earlier, where I was choosing to only display 2 points after the decimal. So I can actually change that as well. I can go to the diagram, scale factors and styles, and I can change this by clicking on the format button and changing the number of decimal digits. I'll just bring this up to 4 and click OK. And now I can see it's 0.0056, which, to remind ourselves, compares very nicely to what we were getting in the hand calculations. So hopefully you found this useful as a great way to validate your hand calculations with structural analysis software. If you'd like to learn more about S-FRAME, please check out our YouTube playlist or go to altair1.com, search for the training, and there are plenty more information available there.